name is Weizman, and today I'm going to give a talk called Dumb Jungle, Can We Trust the UI? I thought we could do this fun little thing where I just posted a tweet, so you can go there, and if you have any questions or like feedback or anything you want to say, then feel free to do so. If you don't have enough time to copy the link, that's OK. Just go on Twitter, find Weizman, and it's just going to be pinned there. So let's get started. So I've been doing cybersecurity ever since I joined the 8200 cybersecurity unit, where I focused on web security, JavaScript security, client-side security. I find the client side of the web very interesting in terms of security. I think it's really challenging securing these aspects. So when I think of security for the web, I think that on the client side, you have a lot of like very interesting types of attacks. You have DOM clobbering, access leaks, CSP bypasses, JavaScript prototype pollutions, CSS injections, cross-site scripting, supply chain attacks, and the list goes on. But what we're going to focus on today is going to be XSS and supply chain attacks specifically, because these two are the ones that provide the narrative of code execution to attackers. And code execution is going to be really important for me to demonstrate what it means to breach an origin of an application. And that's going to be very much in the context of today's talk and in the context of what it means to secure the DOM. So in order to explore this idea, it's really important that we first understand XSS. We're going to do the same thing for supply chain attacks, but first we're going to focus on XSS. So XSS comes from the concept of usability. So usability is a very simple concept, and it was really important from the beginning of the web. So the idea is, being able to use an ecosystem or a programming language or an application or an ecosystem or anything technological. And I think that in context of the web, you can really think of interactions and providing basic user input as the context of usability, especially back then where the web really started. So a very simple example of usability, or to be more specific, user input, you can see here that I can provide some, maybe like my personal name, and then the application is going to be able to reflect it back through the HTML, right? So if we think about usability from the perspective of security, once again, focusing on code execution, then that is how XSS was introduced. So if we do the same trick exactly, but in addition to our personal name, we also introduce some HTML tags that translate to JavaScript code that is, in fact, the code execution narrative here, then we're going to get a code execution narrative, right? So I want you to understand with XSS that this is kind of like an outside type of an attack, and you can see that also in the diagram, right? So you can see here that most of our application is our code, and you can see that we use green to signify that we trust it. So basically, it means that everything that we ship from our servers into the browsers is code that we created, we update, we maintain, and we completely trust. And then the input is the problematic part. That was the case back then when we just started. So our code is something that we trust, and input being provided to the application is the part that we don't really trust. That was the web back then. So to sum up, XSS is really code that should not run within our origin. It's something that is very clear to be able to say. Code that comes from outside is code that should not run, and code coming from within the application is code that should execute. So with XSS vulnerabilities being really problematic back then, we had to catch up as the web security. So I would claim that the web fixed XSS vulnerabilities to a certain extent. Now, I know this is a very controversial statement, so allow me to explain what I mean here. It's not that we're not going to see XSS vulnerabilities anymore. We're probably going to see them for a couple of decades. But what I'm saying is that these days, as opposed to before, the web now provides the tools needed to address XSS vulnerabilities, which was not the case in the past. So if you combine proper sanitization of content being provided in different places in the application, so you can use DOM Purify, or you can even use the built-in trusted type features in the browser, and you combine them with some strong CSP rules that allow you to make sure that strings that are flying into the application cannot translate into running JavaScript code, you can end up in a place where cross-site scripting attacks are eliminated. So I would claim that the web security industry caught up when it comes to cross-site scripting attacks. It's just the builders of websites didn't. And that's really on them, because if the web gives you all the tools that you need to properly secure your application, then the job of the web is almost done. I think that this is a good proof of that. So this is a research posted by Google last year. And you can see here that they did exactly that. They took narratives such as strict CSP, they integrated trusted type, and they managed to get to a point where they encountered 0 XSS vulnerabilities since the introduction of these tools into the web services that they provide as a company. So it's really a matter of being able to do it. The web allows you to do it. It's just a matter of adopting the tools that it gives you. So I would say that input can now actually be counted as something that we can trust to a certain extent, as long as we use the web correctly. And the reason I'm talking about that is because it's a really good comparison to supply chain attacks. Because with supply chain attacks, it's really a whole different story. So in order to understand why supply chain attacks are so complex, I want us to talk about the concept of composability. So what's software composability? So ChatGPT would say that composability is the ability for software components to easily be combined and integrated to create new systems or applications, right? Which is pretty accurate. Now, composability might seem obvious, but what I want you to understand is that it's a really important principle. So an ecosystem or a programming language or technological aspects are far more adopted when their composability properties are successful. And that's really important. So 2 ways to demonstrate that would be, first of all, thinking of development of software. So JavaScript is a well-adopted language partially because its composability features made such a dramatic improvement in the past few years. Because these days you have the NPM ecosystem and packages and dependencies, and because of how easy it is to build software on top of other people's software reliably, JavaScript is really attractive to people to build on top of it. And the same concept is relevant to services. So if you think of services such as Shopify or Figma, they're really good services partially because you have the ability to compose services out of someone else's services. You can build plugins and add-ons, and you can allow other people to adopt them. And that makes such platforms really successful. So composability is a really important principle. Now, what was composability for the web, focusing specifically on the past? So the web was friendly to composability pretty much from the start. So back then, composability came into action mostly at runtime when it came to the web. So you had elements such as script tags, which would allow you to include JavaScript on the fly, or do the same thing with iframes, but instead of JavaScript, include like entire websites within your website. And the powerful feature of that was the fact that you could do so on the fly, in the client side, in the browser. That's really powerful. Think about it, because as a developer of a website, all you had to do in order to compose software out of someone else's software was just dictate this really simple static HTML file. Maybe it had like a script tag or an iframe, and then composability features would fly in the client side. You didn't have to build anything or create anything. The whole thing would just happen on the browser. And that's really powerful. So just to give an example, you can see here that now, in addition to our code, we now have an iframe, for example, that's called bad.com that we include in our application. It's not that we know that it's bad, but it might be bad, and therefore it's written in red, right? So if we look at composability from a perspective of security, then the web kind of had it going also pretty much from the start, because back then there was the same origin policy, which is something that we're going to focus on today pretty much a lot. So the same origin policy focuses on isolating origins from one another. It means that bad.com cannot access assets that belong to example.com, and it goes the other way around as well. So you can see now that from red, we turned blue because the same origin policy now protects our application from bad.com. But when I say access, it's really important to understand what do I mean. So having the exact same example, but maybe a bit more elaborated, you can see here a few things. So once again, we have the example.com website, and it embeds a bad.com iframe. And you can see here that we have storage capabilities, we have network capabilities, and we have the DOM. And each of these websites has its own storage, network access, and DOM. Now, there are many more assets and properties, but we're going to focus on these three, specifically more on the DOM. So just to make sure that we're clear on what DOM means, so DOM stands for Document Object Model, and it's really a static representation, a live representation of the HTML that constructs the website. And by dynamic and live, I mean that JavaScript code can manipulate and update the DOM in the browser at runtime. So that is what DOM is. And each website has its own DOM, but the concept of the same origin policy is that neither can access the other's properties. So example.com can't access the storage of bad.com. It cannot perform network requests on behalf of bad.com, and it cannot access the DOM of bad.com, and it goes the other way around. So that is the same origin policy. So I want to use an analogy, thinking specifically on DOM. So DOM being a tree data structure, I think that for the sake of an analogy, we could use an actual tree. So think of the two domains as two separate trees, the two regions as two separate trees. So if you, for example, have an insect, it might be a bit small, so I just want to make sure that you can see it. So you can see here that there's an insect or a parasite in the bad.com tree. So the fact that it lies on this specific fruit doesn't mean that it cannot just walk around like the different fruits and the different branches and the different leaves. But according to the same origin policy, naturally, this insect is not going to be able to jump to the other tree. That is the whole point of the same origin policy. So now, let's take all that and go and return to the present. So what's interesting about the present is that composability now takes place mostly at build time. So JavaScript, as I said before, is super friendly to composability. It went through a dramatic improvement in the past few years, and that is due to the NPM ecosystem. So you have dependencies, and you have packages that you can consume, and because of JavaScript being the language of the web, it naturally translates to a dramatic improvement to composability on the web. So thinking about the same diagram as before, you can now see that our code is significantly smaller. We still have maybe iframes, but most of our application is now a complex supply chain that's being shipped within into the browser from our servers. And the problem is that it's really hard to tell good code from bad code within a supply chain. So let's explore why. So if we look at the current state of composability from the perspective of security, we're going to find some few interesting things. So first of all, we need to understand that supply chain attacks differ dramatically from XSS attacks. Because if we said before that XSS attacks are kind of like an outside type of an attack, then supply chain attacks are really kind of like the opposite. So they're kind of like an inside type of an attack. They're being constructed at build time, and therefore they're being shipped into the browser being shipped into the browser as part of our application into the origin that we trust of our application, which means that they could include a lot of things that we don't necessarily trust. We can't really trust our application anymore due to that. So supply chain attacks are really code that we don't even know whether we can trust or not to execute within our origin. Also, not only that that's the case for supply chain-based development, but it means that that's the case for more than 90% of the code that we ship into the browser as part of our application. Most of the code of web applications today is being constructed as part of a supply chain out of other people's code that we don't know, we don't trust, we can't control, we can't understand when it's being updated to the fullest extent, and that makes things really complex. And the worst part that we're going to focus on today is how the web isn't even ready for this. Because we need an increase in the resolution in which we isolate and enforce isolation between entities that live within the origin. So think about how the same origin policy is excellent, but it's no longer the only thing that we need. We need to be able to isolate entities living within the origin that we trust. We need isolation between the dependencies that construct the supply chain. We need isolation between the scripts that are being shipped into our origin. So before we move on to the implications, I just want to sum this up. So as we said before, the same origin policy means that we have isolation between origins. So bad.com can't access example.com and vice versa. But this also means the exact opposite. It means that there is no isolation to any entities whatsoever that live within one single origin. So bad.com, any entity, whether it's a DOM node or a JavaScript script or parts of the storage, all of them within bad.com can access all of the rest within bad.com. And it also means the same thing for example.com, which is the application of ours that we are trying to trust. So the equation that I want you to remember here is that when you don't have an isolation mechanism within a single origin between the entities living within it, and you combine it with a really complex supply chain that's being shipped into the browser by your application, by your servers, you're going to get a really big mess. So now to talk about the implications. We're going to focus on DOM today, but before that, I just want to give you a really quick example on how this affects storage in a very simple example. So do the following thing. Visit web.telegram.org, the famous telegram.org. Log in. You just copy the local storage, and then you open a tab in which you're not logged into Telegram, and then paste the local storage as is. When you refresh, you're going to learn that you're logged in to the application. Now, this is wild. Why is this wild? It means that if we can do it manually like this, it means that any JavaScript running within your origin can do the same thing. Now, Telegram and the rest of the world aren't really worried about this because they trust the code that they provide through their origin. But as I'm trying to say, this is no longer the case. We can't trust what we're shipping through the origin. This is just like a very simple example of the keys that you can just copy and paste, and you're going to find out that it's a mess. Now let's talk about the DOM. So the DOM is kind of a jungle, right? It's really good at isolating DOMs from across all regions. So one DOM of an origin not going to be able to access the DOM of another origin. But within one single origin, it's kind of a jungle. It really all comes down to encapsulation. So this is something else that we need to understand here. Encapsulation is a way to restrict the direct access to some components within an object. Now, in order to demonstrate encapsulation, JavaScript is actually really good at secure encapsulation of information because of its well-known feature called scopes. So, pretty simple example. You don't really need to understand the whole thing, but what you need to understand is that by creating a function and allowing it to have access to some variables that store information, whenever that function is going to be invoked, it's going to have access to that information. And if that information is being stored within the scope, then no other entity outside of this scope, no other JavaScript code is going to have access to this information. Scopes in JavaScript are secure. You can use them safely. So if, for example, you fetch some sensitive information from the server and you want to use it on the client side, if you store it in a scope and then teach the function that you manifest to just use the information that's accessible to it within the scope, you can rest assured that it's going to be safe. It's really a matter of how you're using it, but we're not going to get into that today. But imagine that we take this sensitive information and we attach it to the DOM of the application, because maybe the user needs to be able to interact with it, right? So the DOM is actually really bad at safe encapsulation. In fact, it doesn't support safe encapsulation whatsoever. Part of it is because there's no isolation between DOM nodes, so you can jump from any one node to any other node within a single DOM tree, and there's nothing that can stop you from doing that. And even if you try to implement JavaScript solution virtually at runtime, the DOM is such a mess, design-wise, that it's just not going to allow you to do it. It's just too easy to bypass it. So effectively, you can jump through different nodes within a DOM node, within a DOM tree, really easily. Obviously, as long as they're attached. If they're not attached, then it's going to be a bit more tricky, but we don't really care about nodes that aren't attached. And this applies to iframes as well. So you can jump from one node of a DOM tree of an iframe to any other DOM node of a DOM tree of any other iframe. Obviously, as long as they share the same origin, but if they do, that's kind of like the case. Why is this important? So I want to take the example from before and then reapply it. So if before we were concerned about the termites living within bed.com, but we didn't really care about them because they couldn't jump off to example.com, the paradigm in which I'm referring to, the problem that I'm trying to describe, means that the parasites, in fact, live within your tree. They live within example.com, which is our website, and they come from within it. And then if there's no way to stop them from moving across the different parts of the tree, then the whole origin is, in fact, compromised. That is the problem that we're trying to address here. So why does it matter? Why do we care about DOM encapsulation so much? So a lot of reasons, but I'm going to give two straightforward examples. First of all, attackers can read from any parts of the DOM. This means that once the user introduces sensitive information into the DOM, any other entity running within your origin can read from the DOM, and there's nothing you can do to stop it. So like the simplest example, if I insert my email address, then an attacker can implement code that leverages the API of the DOM to just access any parts of it and just steal my email address the minute it's being introduced into the DOM. And there's nothing we can do about it. And also, the right part of it is also part of what I'm worried about, because it also means that you can easily phish users, because you can convince them to interact with things that you introduced into the DOM as an attacker instead of what the application expected you to interact with. And this actually happened in real life. So without going too much into it, I don't know how many of you heard of the well-known Mage Cart horror group, but these guys basically managed to breach a lot of supply chains of really big websites. One of them was Ticketmaster. And they used that to compromise the entire origin almost completely. So what they did was to convince the user that they're interacting with a legitimate part of the DOM that, in fact, convinced them to introduce credit card information, and they just stole it and leaked it to their server. So these are the bad things that can happen once your supply chain is breached, and defending and securing your supply chain is really complicated. So I want to give you a real-life example, and I'm going to show you a cool demo, hopefully to get my point across. So I work for MetaMask. MetaMask is a self-custodial crypto wallet, which means that we store the private key associated with the user within the browser locally. Now, what you need to understand about the world, unless you're talking about MPC, what you need to understand about crypto wallets is that if your key is compromised, then it means that your assets are compromised as well. Now, this means, in fact, that makes MetaMask really obsessed with client-side security, because we don't really have a server that helps us defend the private key, and the private key is supposed to be completely safe on the client side. So it's our job as security engineers to make sure that we can secure the key completely without leveraging any server-side capabilities, and doing so only on the client side. And the crazy thing is that we're not worried about cross-site scripting at all. Because, as I said before, the web gives you all the tools you need to address XSS attacks, and we managed to get to that point. We're using CSP and trusted types and everything that we need to make sure that XSS attacks couldn't happen. And obviously, things could go wrong potentially, but so far, so good. But composability security risks, on the other hand, are terrifying to us. And we definitely need to find a way to address those. So that is really what the LavaMoat project is all about, which is part of MetaMask. So we focus on creating JavaScript security tools for JavaScript. And a lot of them focus on exactly that, being able to enforce isolation between entities that live within one single origin. Because of how the web doesn't allow us to do this naturally, we're trying to solve this on the user end with implementing JavaScript code. So we have a lot of interesting tools. You have LavaMoat, Snow, Scuttling, LavaDome, a lot of things that we're focusing on. But today I want to focus on LavaDome, because LavaDome is the version that focuses on the isolation relevant to the DOM. It focuses on isolating parts of the DOM tree and making sure that no one has access to them, except for the user, for the user being able to interact with these parts. So everything's going to be a bit more clear once you see the demo. There's supposed to be an image. Great. So the demo is pretty simple. Here I have the MetaMask browser extension, the crypto wallet that I referred to. And as I said before, we have a private key that's being stored within the browser, right? So one thing that you can do at any point is just ask MetaMask to show you the private key if you want to see it, interact with it, copy it, export it, whatever. So if I do the following thing, I'm going to be able to see my private key. You can try to steal it, but it doesn't really matter. But go ahead. So now, what's the problem here? As we said before, you're going to learn that once this is attached to the DOM, any other entity, any JavaScript code, any DOM node would have access to this part of the DOM. And that is the problem that I'm trying to demonstrate. So an attacker can just run the following line, and it could just find it right here. You see that it's being there? So this is the problem that we're talking about. And it's really obvious. Like, this is how the web is designed. Anything that's being written to DOM can be read from it at any point. That's fine. But since we don't trust the supply chain, that's something that we want to solve. So I have here this feature flag that activates, for the sake of the demo, the LavaDome, the project called LavaDome that we created and integrated into the application. So we're going to do the exact same thing. And you're going to see that nothing really changed. You can still see it, you can still copy it, you can still do whatever you want. But this time, it's not going to be here. Now, for those of you familiar with the web, this is kind of wild. Like, the fact that you can draw information to the DOM, but not allow JavaScript to have access to it, is something that the web doesn't allow you to do, doesn't support, and it's exactly what we're trying to focus on. Now, implementing this in JavaScript is really challenging, and it works pretty well, but it does have a few very sophisticated vulnerabilities that can bypass it. And it's obviously going to be a journey, so we're going to focus on patching those, but so far it seems kind of promising, I guess. But these are the types of things that we're focusing on trying to make the community understand. Like, this is important. Being able to do this is important, and it solves a real use case, because we understand the implication of not trusting our origin. We don't trust our origin. We understand that the supply chain of our origin can be breached at any moment, and we take actions to try to avoid it. So if there's part of the supply chain that was breached, as opposed to before, now if an attacker is going to wait for the user to ask MetaMask to draw this information, this sensitive information, to the DOM, back then an attacker could just steal it and leak it and compromise the wallet completely. But now it's no longer possible. So that is the power of LavaDome, and that is the power of thinking about the problems that are relevant within the security risks that lie in composability. So back to where we were. So this is pretty much the end of the conversation, and we talked about a lot of things, so I kind of want to summarize my perspective of what should be the key takeaways. So these days, web apps are mostly code not maintained by us. We don't understand when they're going to be updated, and we can't really control the code that's being run in there. Now, it's really good for composability. This is great for the ecosystem. This is great for the web. We want composability to improve, and it really attracts people to build in the JavaScript and the web ecosystem. So that's definitely good. It's just, it's really bad for security. And the web does not take into account the gap between composability and the security needed to safely secure these parts of the web. Because the web really focuses on isolating origins from one another, but the point I'm trying to make here is that we can't trust entities within a single origin. So we need isolation in a higher level. We need isolation between DOM nodes. We need isolation between script tags. We need isolation between storage partitions, being able to perform network requests, being able to execute code. We need to be able to apply kind of like a same origin policy for deeper entities within an origin. Otherwise, it really puts all assets under risk, whether they're storage, network, DOM, all of them. Now, we should have kind of like a same origin policy, but for parts of the DOM. If we focus on the DOM specifically, then I would claim that it would be really useful if we could isolate parts of the DOM. because then we'd be able to defend against the attacks demonstrated before. So we could defend from entities we don't trust from accessing sensitive parts of the DOM. And we can also make sure that they don't have permissions to manipulate and change the DOM that the user interacts with. But what I want you to take with you, and what I want you to think about, is how we could not only solve these issues that we talked about today, but we could also unlock new levels of composability for the web if we had these features. So think about what new technologies could we invent if we could create safely encapsulated DOM components. Imagine that we can create really interesting components, really interesting code, and if an application could trust it to do potentially problematic things, but we're not going to have to worry about it anymore because we know it's being safely embedded into the application, then try to think about the possibilities, what we could build with that, and how well it will do to the composability properties of the web, which made such great improvement and should continue to do so. That was pretty much it. Thank you.